Hi everyone. So welcome to the exercise class. So my plan for today would be to talk a bit about all the problems that you have in the exercise sheet for this week. So you're gonna have 4 exercises. So the first exercise will be about the wave function in 3 dimensions, because before that we were only talking about wave function like on the one axis x, and now we can go to the 3-dimensional case, and you probably already did in the lecture. Then another exercise will concern the parity operator, which is a special operator with some interesting properties. Then I'll talk a bit about Gaussian wave packets, like a specific kind of a wave function. And finally, the last exercise is about teleportation. So for that, I also thought it would be useful to recap a bit like what we know about quantum circuits and how to operate with quantum circuits, since that will be like an important part of the course. Okay, let us start with the wave function. In 3 dimensions. So how do we define the wave function? Well, in 3 dimensions. So it means that our wave function now would not only depend on x, but also on y and z, which are the coordinates. And we can just call it psi of r. And to see how this relates to the representation of the wave function with respect to x, y, and z directions, let us rewrite psi as just like identity acting on x, identity acting on y, and identity acting on z. So the idea is that the 3-dimensional wave function can just be seen as a wave function of 3 subsystems. So one of subsystems is the x direction, the other corresponds to the y direction, and the third one corresponds to the z direction. And here we do the trick. We just expand the identities in the x, y, and z bases respectively. X, tensor product, now the identity on y, tensor product, the identity on z, and psi. And psi is in x, y, z. So then what we get, then what we get is the following. dx, dy, dz, x, tensor product y, tensor product z. These are just the kets. And now the bras are x, y, z, acting on psi, y, z. And this is what we will call the wave function in this xyz representation. So essentially, in the end, if we call this ket, the tensor product of this kets of xyz as r, xyz, then essentially what we just get is this triple integral dr psi of r, r, x, y, z. Okay, and in the exercise, you also need to go to the momentum representation of this wave function, and the procedure is the similar as we do it in one-dimensional case. So I'll just start it here, and you can continue it by yourself. So we call the momentum wave function in momentum representation as usual psi bar of p, and P now is a vector. Then this is just this bracket of P with psi. And the bracket, the bra of P can be just written the same as the bra for R as a tensor product of corresponding momentums in X, Y, and Z directions. Acting on psi. And then psi we write as we've written above. So what we get is this stays. And instead of this, we write the integral dr psi of r, r x, y, z. And r x, y, z we can write out as just x, tensor product y, tensor product z. Okay, and continuing to write this out, what we get, and putting the corresponding bras in the tensor product to corresponding kets in the tensor product of R. So we just need to put this one together with this one, Py with Y, and Pz with Z, because they are the ones which live on corresponding Hilbert spaces. We arrive to the R, psi of R. Then here we have Px, x, Py, y, Pz, z. And for each one of these, we know the exact relation. So as we remember, like they're connected. So Px is a Fourier transform of x, Py is a Fourier transform of y, and so on. And here we can insert the corresponding equations for 1D. And then in the end, what we will get, I'll just leave it as an exercise. We get the following. dr psi of r e to the power minus I pr over h. Yeah, as I mentioned before, in principle, you can, from the beginning, take h bar equaling 1. That is also a completely acceptable solution. But here I just keep it just to make sure that the units are fine. But you can also take that h equals 1. Okay, and further in this exercise, you just have to prove some things which are which you already know for 1D, that hold for 1D. For example, the commutator between P and X is IH, and so on. But just kind of generalize this results to the 3D case. So how Px, Py, Pz act on psi of r. They're actually just the corresponding partial derivatives by x, y, and z with the coefficient minus IH. And also look at the commutators, such as, for example, x, y, so on x, px, where x and px would already be not the operators acting in one-dimensional case that we looked at earlier, but in the case where we're looking at the wave function in 3 dimensions. Okay, so these exercises are quite straightforward. You just have to apply the same rules that you did in a one-dimensional case that we looked at earlier. Okay, so the second exercise is a bit more fun. So it's about parity operator. So the parity operator is a following operator. So it acts on a function psi of x in the following way. So it turns psi of x to psi of minus x. And correspondingly, it acts on the ket on the state x as it brings it to the state minus x. And the first thing that we have to find out, what is the continuous representation of this operator? Like, as you've seen in a lecture, the continuous representation is just, so it's called p of x prime in this case, and it's just the value of p when it's squeezed between the x and x prime. So this continuous representation can be just understood as going back to the finite, from continuous case to finite dimensional case, as just the elements of the matrix that would correspond to the operator p in this x representation. But here it's just this, this matrix in a way continuous. So these are kind of matrix elements of p. And why is this useful? Well, where this continuous representation comes in handy, where imagine that you're acting with the operator p on the state psi, and then you want to find out kind of which representation this new state that you got with acting with p and psi has. So then you just write it out as, so we have x, then there is an operator p, and then we can write out psi in terms of the x basis, which is psi of x prime, dx prime. Then what we get is psi of x prime, x p, x prime, dx prime. So we have psi of x prime, p of x prime, dx prime. So if we have the continuous representation of the operator, then essentially we don't have to work with kets and pros anymore. We can just work with this continuous representation if we have already the corresponding, so the corresponding representation of the wave function psi. Then we will know how exactly this operator acts on the wave function. So this is like why we need the continuous representation. And so you have to do this for this operator p. And yeah, it's quite a simple calculation. You'll get some, as a hint, you'll get some sort of delta function in the end. A more interesting question is, why is this parity operator useful? So for this, we need to look at its eigenfunctions. So the eigenfunctions of the operator p, or eigenstates of the operator p, would be these functions which, if you act on them with the operator p, you get them back with their corresponding eigenvalue lambda. And again, like going back to the x representation, what we get here would be this. And essentially, here we would get that psi of minus x would be equal to lambda psi of x. And this has to be true for all x, right? So what conclusion we can make from here? So this since this has to be true for all x, then there are only two options of the function psi, or like, yeah. So the first option is that psi of x is even. So psi of x equals psi of minus x. This corresponds to lambda plus 1. And the second option is psi of x is odd, which means that psi of x equals minus psi of minus x. And the eigenvalue is minus 1. And this means that the parity operator, it allows to distinguish between even and odd wave functions. Just between even and odd functions. And this might come in handy later when, for example, when you're dealing with the arbitrary Hamiltonian in a Schrödinger's equation, then if you see immediately that the Hamiltonian commutes with the parity operator, then this means that the parity operator and the Hamiltonian have the same set of Eigen functions, which brings us to the conclusion that we can, when looking for the eigenfunctions of the Hamiltonian, to find out the energy levels and the solution to Schrödinger's equation, we just need to look at the even and odd functions. We can just separate our search for this even and odd functions. Okay, so this was a parity operator. Then the third point are the Gaussian wave packets. Yeah, so we have certain conditions for the wave functions that we have, right? We can have, so they have to be continuous and they have to be normalized from minus infinity to infinity. However, like they can take, of course, they can take different functions can be used to describe different wave functions. And one of this kind of useful one of the useful descriptions types of the wave function is this Gaussian wave packet, which you can think about it as just something like a small wave, which is approximately confined to a certain to a certain interval on the x-axis, and then it's just moving along x-axis in a way, and then it starts to widen or to thicken and so on. And usually, to describe such a packet, we first need to define so-called an envelope function. So it is a function which determines the outer shape of the wave. So this is an envelope function. And this is, for example, this wave function. And essentially this envelope function, it's used to kind of bound the function. So it just tells it about the shape, the outline. And the wave function psi of x is just then this phi of x e to the power ikx. So the Gaussian wave packet is the wave packet for which the envelope function is as follows. It is a Gaussian. So here we're looking at the Gaussian, which is peaked around the point x0 and has like this width here proportional to sigma. And then the wave function psi of x then can just be written as this Gaussian by e to the power ikx. Okay, and this Gaussian has a number of Gaussian wave packet has a number of interesting properties. So the first one that we have to show is the first question that we have to answer is, how does the momentum wave function look like? So as we remember, the momentum wave function is just the Fourier transform of psi of x, right? So to find out psi bar of p, we just need to carry out the Fourier transform. So this is quite a lengthy integral to take. So I won't probably do it all of it now, but I can tell you how to do it. And another comment would be that I also got some questions about it. So you encounter in the course some integrals which are not so straightforward or not so fast to take, though most of them are takeable by hand. But like at the exam, you will not be required to to be able to take these integrals by hand, essentially. So probably there will not be any problems at the exam which would require an ability to take lengthy integrals by hand. So it's fine. I mean, however, it's nice to know like that some of these techniques exist. But I think like most of the integrals in this exercise class, you should have seen them in analysis at some point. So here we just insert our Gaussian. Then we have kx minus I px over h dx. Okay, and here the idea is that to solve this integral, one thing that you immediately have to see is that this is an integral of the form where you're trying to integrate something like e to the power minus x squared, and from minus infinity to plus infinity. And this is exactly the Gauss's integral, which tells us that the integral from minus infinity to plus infinity of e to the power minus x squared dx is square root of pi. So this is, I will not prove this here because I think it's a well-known fact from analysis, and also it's you can look up the proof of how to do it like on Wikipedia. I think it's quite funny proof. And as soon as you see that you have an exponential of something that can be brought to the to be a full square of something, then you immediately have to think about this Gauss's integral. And here what we have in the exponential is this sigma squared plus, write it like this, plus I x p Let me write it this. So minus ix p minus k over h. Oh, sorry, hk over h. And what is this? So actually, yeah, maybe we do first the substitution here. So here we can do the substitution, which is we can substitute x minus x0 to x. And we can do it, and the bounds of the integral will not change. The x doesn't change. Here, however, we get the following exponential, will be minus x squared over 2 sigma squared minus I x plus x0 p minus hk over h. Okay, and then what we want to do is we want to look at what is in the exponential, and what we have here is, so I'll now do without the minuses, so I'll just do x squared over 2 sigma squared plus I x plus x0 p minus hk over h. This would be, we have a constant here with x0, which we can just take out of the integral. So this would be I p minus hk over h x0 plus we have x squared over 2 sigma squared plus I x p minus hk over h. The first component in the expression stays, and then this component we can write it as x squared plus 2 sigma squared I x p minus hk over h over 2 sigma squared. And now we just have to add add the component here, which would complete this part to be a full square. So this would be, we have x squared plus 2 sigma squared I x p minus hk over h minus, because we have an I, sigma to the 4 p minus hk squared over h squared over 2 sigma squared. And then we just have to add it here again. And what we get here is plus p minus hk squared sigma squared over 2h squared. Okay, great. Then essentially we just can write it out then as the following: I p minus hk over h x0 plus the full square that we have here, x plus I sigma squared p minus hk over h squared over 2 sigma square, and minus, again, a constant with respect to the integrated variable, which is x, to h squared. Okay, and now if we insert it into integral, into the integral, we get then that psi bar of p that we're looking for is like our coefficients that we had before. Then the exponential from this part. Zero. Then again, another exponential that we don't have to integrate over this one. And then finally, the integral from minus infinity to plus infinity of the full squared. Okay. And again, you have to do here to compute this integral and to bring it to our usual Gaussian integral of just e to the power minus x squared, you have to first shift the x, and then you have to scale it with respect to the coefficient here. And then you'll get like just the square root of pi with some additional factor. But and also this factors here, which are accumulating. But in the end, what you get is something that is proportional to the exponential of minus p minus hk squared sigma squared over 2 h bar squared. And essentially, this is, again, a Gaussian packet, but with respect to the variable p. And the idea here is that, which also translates from the mathematical idea of the Fourier transform of the Gaussian function, is that if you transform a Gaussian wave packet from the position basis to the momentum basis, you will get, again, a Gaussian wave packet. The same as in mathematics, if you Fourier transform the Gaussian, you'll get the Gaussian again. Okay. So I hope this derivation of the integral was comprehensive. What you also have to find in this exercise is what are the expected values of h, p, h squared, and p squared. And the procedure is as follows. The procedure is just the same as we did now. So first you shift the x by x0, and then you arrive to either a Gaussian integral or like one of the like other derivatives of this Gaussian integral. So for example, if you calculate x, the expected value of x, then this is just this. And in integral form, this would be psi conjugate x, psi of x dx. And yeah, to calculate this integral, you will need to know only 3 integrals. So essentially the first one is this, as I already mentioned. The second one is minus infinity plus infinity, is x e to the power minus x squared dx, which is actually 0 because x e to the power minus x squared is an odd function, and if we integrate it from minus infinity to plus infinity, it will give us 0. And the third one is x squared e to the power minus x squared dx equals square root of pi over 2. So yeah, so these are the only 3 that you will need. Okay, and I would recommend to calculate p, the expected value of p, in the basis of p. because then the calculation becomes very similar to what you would do to find the min value of the position, because as we just established, the Gaussian wave packet has the same form with respect to the function, both in position and momentum basis. So here you would just calculate it as psi bar p conjugate p psi bar of p dp. Okay, and the same for p squared and x squared. I know that this is quite a lengthy exercise in terms of calculation. You're also totally allowed to use Mathematica or MATLAB or whatever software you have. Again, you're not expected to take these integrals by hand, unless you want to, unless you feel nostalgia for analysis and want to play around with these exponentials for some time. Okay, so then you have to p squared and x squared. And for, just to give you an intuition, for example, for the expected value of x, you might already know what result you would get, because we're looking at the wave function, which is concentrated in this Gaussian wave packet, and the Gaussian wave packet is peaking around the value x0. So you can say that it's x0. Or, for example, with p, you can also have this kind of intuition, because we're looking at the wave packet, which has a wave number k here. So the wave itself is kind of moving with respect to k. So you can already say, then I can expect this p to be hk momentum, the expected momentum. I mean, again, I repeat that in principle you can take h equals 1. Then it's just k. For x squared and p squared, it's a bit more problematic to guess in the beginning what values you will get, but yeah, for x and p, this is quite straightforward. Okay, and now we come to the final part, which are the quantum circuits and teleportation. So, yeah, I just thought that it would be useful to repeat some things about quantum circuits, since you've seen them in the lecture and also in exercise class, but maybe it's a bit too fast, and maybe you're not completely comfortable with them yet. So, if we give a formal definition of quantum circuits, it's just a cyclic network of quantum gates, which are connected by wires. So you just have a bunch of quantum gates, which we usually draw as like squares or some more complicated structures here. Yeah, so it's just a sequence of these, and each quantum gate, it represents a certain operation, like this one, or this one, and each wire represents 1 qubit. And then if you go in a vertical direction, these are just the qubits that are involved in performing these operations. And if you go in the horizontal direction, this is just the kind of time or the order of application of the operations. So so quantum gates just represent the operations which are carried on qubits, and wires represents qubits on which the operations, so these gates, act. The size of quantum circuits is the number of gates plus the number of qubits that are involved in the circuit. So when finding some circuit which performs a certain quantum algorithm, it's both important to minimize the number of qubits that are involved in the operation, but also to minimize the number of gates that are involved. So the gates can act on 1 qubit. These are 1 qubit gates, which are, for example, in theory, most commonly used ones are the Hadamard gate, X gate, for example, Z gate, and so on. And one has to take into account that this theoretically popular gates, they're not always directly implemented or implementable even on hardware. So usually, if you look at the papers in quantum computing where people actually try to implement the certain circuits on their quantum computers in the lab, then they would use a bit different sets of gates. For example, there is this Soren-Murumson set of gates, or this T gates, and so on, which are just gates which are implementable on the hardware. But since we're like working in the theory, we can just work with this like theoretic gates and build our circuits with them. So for each of these gates, like for example, Hadamard, X gate, a Z gate, it is, of course, they all have a matrix, 2x2 matrix, which corresponds to them in 0-1 basis of the qubit. But it's enough to remember how they act on 0 and 1 states. So for example, if the qubit is in a 0 state, then the Hadamard puts it in one in a superposition of 0 and 1 states. So 1 over square root of 2, 0 plus 1. And if it's in 1 state, then it puts it in the superposition of 0 and 1, but also with some phase on 1. So this state is actually called plus, this state is called minus. So X gate is a flip gate, so it performs a bit flip. So if we start with the 0 and we act with the X gate, it puts it into 1. And if we start with 1, then it flips it back to 0. And the Z gate, it takes 0 to 0, nothing changes, and it takes 1 to minus 1. So it just adds a phase in case the state of the qubit is 1. And sometimes to know these two transformations, so how the gate acts on the 0 and 1 state, is enough to characterize the gate. And sometimes to remember these things is handy because then you can just analyze the circuit quite easily, what happens in the circuit. Then there are 2 qubit gates, out of which the most famous is C0. And C0, it performs, it can be seen as being similar to what is done in the classical computation with just the bits, because it performs a sort of a logical operation. So it acts in following way. So for example, we have both qubits in a pure state, like x and y. Then we act with C0, and in the end, I have here would be x, and here would have x plus y. So the sum of the two bits that kind of these two qubits represent, modulus 2. So to know how this gate acts, you just need to keep in mind that, for example, if both qubits start in state 0, we apply C0, then nothing changes. If the first qubit is in 0 and the second one is in 1, and we apply C0, then we get 0, and here the 1 still stays because 0 plus 1 is still 1. Then if the first qubit is 0, sorry, the first qubit is 1, the second one is 0, we apply a C0, then this stays 1, and this one flips because 1 plus 0 is 1. And finally, if they're both starting in a state 1, then we have here 1, and here it flips because 1 plus 1 modulus 2 is 0. Okay, so the idea of the C0 is that it flips the flips or doesn't flip the state of the second qubit depending on the state of the first qubit. So if the state of the first qubit is 0, like here and here, the state of the second qubit stays the same. If it's 1, like here and here, the state of the qubit flips, the second qubit flips. So a good example to look at here would be what happens if the state of one of the qubits is not pure. So if the state of one of the qubits is, for example, a superposition of 0 and 1, right? And the second qubit is 0. Okay, then we have to kind of combine two cases. So the first case being this one, and the second case being this one. So suppose that we apply C0 to the 0 plus 1 square root of 2 tensor product 0. What we arrive to, we apply C0 to 0, 0 plus 1, 0 over square root of 2. So if we act with C0 on 0, 0, we know that nothing happens. If we act with C0 on 1, 0, we know that it turns to 1, 1, according to this picture here. So what we get is 0, 0 plus 1, 1 over square root of 2. And this is actually, this state is that we got here, 0, 0 plus 1, 1 over square root of 2. It's one of the states in so-called Bell basis. So Bell basis is a basis for the system of 2 qubits. Okay, so of course one can also come up with, like, for example, 3 qubit gates. For example, analogical to the C0 for the 2 qubits, one can also construct CC0 when we have the state of the third qubit controlled on the state of the first 2. This is a CC0 gate, also called a Toffoli gate. And if we have here incoming X, Y, Z, then it transforms it to X, Y, and sorry. And the state of the third qubit we described as end x y plus z. So essentially, nothing happens, no transformation happens here unless both x and y are in one state, then the state of the third qubit flips. Yeah. Then another, of course, then one can come up with some logical analogs to the classical computation gates, to their analogs in quantum computation. But these are the gates that I just showed you. They're the most used ones in the, at least like in theoretical descriptions of the algorithms. Okay, and then finally, we have another point in the circuit, which is a measurement, which is usually denoted as like the sign here. So this corresponds to the measurement of one qubit of the corresponding qubit in 0-1 basis, which is also called a computational basis. And yeah, one small correction. Like sometimes, because after the measurement, the state of the quantum system collapses to one of the states which correspond to the measurement projectors, then the system becomes, with the respect to this measurement device, kind of classical. So after the measurement, it is in the measured state with certainty. So because of that, sometimes after the measurement, the wires are it's not a single wire that's drawn, but a double wire. So this is kind of a classical wire. And one single wire is a quantum wire. Just a notation. And with a measurement, for example, let us look at the following circuit. Suppose we have a qubit which starts in the state 0. Then we apply a Hadamard. And then we perform a measurement. Maybe then the circuit continues. Okay, so let us analyze. So first, if we apply a Hadamard to 0 state, then just before the measurement, the state is 0 plus 1 over square root of 2. And then we measure in 0-1 basis. Then essentially with 1/2 probability, we get 0. With 1/2 probability, we get 1. Okay. Perfect. Then, so this was about the circuits. Now let us come back to the exercise. So the exercise will be on teleportation. And here we will learn that the entanglement between two parties is a useful resource if you want to kind of teleport, in a particular meaning of that word, the state from your lab to someone else's lab. Okay. So the idea is the following. So suppose that we have Alice and Bob who share an entangled state. So the state just lives in a Hilbert space, in the tensor product of their Hilbert spaces, HA by HB. And they share this entangled state that we already seen before, which is, as I said, one of the Bell states. 1 over square root of 2, 0, 0, AB plus 1, 1, AB. Okay, and then also Alice has a system S. In state phi S, we will call it. And we can just already write it as superposition of state 0 and 1. But we don't know the coefficients. Alpha 0s plus beta 1s. And then suppose that Alice goes away from Bob, so they're spatially separated, but they're still they still share an entangled state. So Alice goes away to her lab, and she still has an access to the systems A and S in her lab, and she measures A and S together in Bell bases. Yeah, I'll come to this a bit later. But essentially, this just means that she measures these two qubits in a joint basis for two-dimensional systems, for two qubits. Yeah, for two two-dimensional systems. And she gets some results, right? Then what she can do, she can classically communicate this result to Bob. Just send him an WhatsApp message. And then, depending on this result, Bob still has access to the system B in his lab, which was at some point entangled with the system A that Alice has. And Bob gets a message from Alice, and then Bob applies an operation to qubit B based on the depending on the result that depending on the message he got from Alice. And then voila, he gets exactly state phi on his side. The same state that we started with for system S with coefficients alpha and beta, he gets it on his side. So this is kind of a teleportation of not like a state, but like information about a state. Okay, so now what we'll try to understand in this exercise is like what exactly happens and which operations Bob has to apply on his side, depending on Alice's message, to get the state phi. Like a useful analogy that one can make with for example, the quantum with just classical computing or cryptography is that to see the entanglement as like this one-time pad or this one-time kind of code that A and B share, and then A can go away from B and send him just some results that she locally has obtained about the system S, and then B, just because he kind of has this entanglement, has this encryption key, he can encrypt the information that Alice has given to him and put it into relevant form, as in here the information about the state of S. Okay, so now let us draw a quantum circuit which would correspond to this situation. So we have first A and B. suppose that they both start in state 0. So first they have to create an entangled state, 0, 0 plus 1, 1, between two of them. And this is exactly something that we saw in the example that I've given. So first we apply a Hadamard, then we apply a C0, like back here. What's this? Yeah, here in the bottom of the page. Because after we apply a Hadamard, then the state of A becomes 0 plus 1 over square root of 2. And after we apply a C0 to A and B, it's 0, 0 plus 1, 1 over square root of 2. Okay, then B stays. Then A goes away. I suppose like this is space. This is time. And in her lab, she has system S in state phi S. She went away, and she measures them in Bell basis. Then there is some kind of classical outcome. Because it's classical, I portray it with the double wire. This turned out to be quite wavy. Let's make it a bit more straight. Yeah, and based on this classical outcome, Bob applies some operation U, unitary on his side, and gets phi B. Perfect. So let us come to the details. So first, what does it mean when I say that Alice performs a Bell measurement in a Bell basis? So first, what is Bell basis? So Bell basis, as I already mentioned, is a basis for 2 qubits, for a system which consists of 2 qubits. And now I will write it in terms of computational basis of each of the qubits. So it's 4 states, which are 0, 0 plus 1, 1 over square root of 2, 0, 0 minus 1, 1 over square root of 2, 0, 0, 1 plus 1, 0 over square root of 2, and finally 0, 1 minus 1, 0 over square root of 2. Okay, great. So we have this basis. However, it is still unclear what it means to measure in this basis, especially operationally, because I just, as I said, the measurements in a quantum circuit correspond to 1 qubit measurements in their 0, 1 basis. So how do we arrive from being able to measure in each individual qubit in 0, 1 basis to measuring in the Bell basis? Okay, I propose the following scheme. So we want to measure in Bell basis, but we still can only measure single qubits in 0, 1. Okay, I propose a following scheme. To understand the scheme, we first need to understand how to get Bell basis states, all those 4 states that are listed here, if we just have qubits in 0 and 1 states. So as we already seen, if both qubits start in state 0, and we apply a following procedure with Hadamard and a C0, then we arrive to 0, 0 plus 1, 1 over square root of 2. Great. Let me copy this to the next page. So I would need to again. Yeah. Okay, great. Then another question is, next question is, okay, what if I have qubits which starts in state 0 and 1, but I apply the same combination of operations? Hadamard and a C-note. Then here up to this we get 0 plus 1 square root of 2. Then we need to apply C-notes to 0, 1 plus 1, 0 over square root of 2. Right? Is this correct? See. 0, 1. Ah, sorry, 1, 1. Yeah, I was thinking something went wrong. Yeah, plus 1, 1 over square root of 2. And if we apply C-note to 0, 1, nothing changes. If we apply C-note to 1, 1, then because the state of the first qubit is 1, the state of the second one flips. So we have 1, 0 over square root of 2. Okay, that's another Bell state. Fine. I think we already can start seeing a pattern here, but let's continue. So what if we start with the first qubit in a state 1 and the second qubit in a state 0? Same sequence of operations. Then after the Hadamard, here we get 0 minus 1 over square root of 2. And after a C-note, which we apply to 0, 0 minus 1, 0 over square root of 2, we get 0, 0, nothing changes, minus stays. Then 1, 0 gets the second qubit flipped to 1. So we have 1, 1 over square root of 2. Okay, another Bell basis state. And finally, if we have these two qubits starting in the state 1, then we apply a C-note to 0, 1. Sorry, no plus here. Minus 0, 1 minus 1, 1 the square root of 2. We get 0, 1 minus 1, 0 square root of 2. So the operation, so our conclusion is that this operation of applying Hadamard and the C-note gets us from computational basis to Bell basis. And and each combination of the qubits in a computational basis, of the states of qubits starting in the computational, of the states of qubits which start out in a states of the computational basis. So for example, 0, 0 corresponds to the 0, 0 plus 1, 1 with square root of 2. Then 0, 1 corresponds to 0, 1 plus 1, 0 over square root of 2. Then 1, 0, it's 0, 0 minus 1, 1 square root of 2. And finally 1, 1 is 0, 1 minus 1, 0 over square root of 2. So this is the operation that allows us to go from Bell basis to computational basis. Okay, then if we reverse this this circuit, which we can do because in a very straightforward way for two reasons. First, both operations are unitary. Second, moreover, both operations are Hermitian, which means that they are their own inverse, which means that if we start with a Bell basis, and apply first the C0 and then a Hadamard on the first qubit, then we arrive to computational basis. Okay, so which means that kind of this arrows here, they also reverse if we apply this operation, which means that if we start with the Bell basis state and apply first the C0 and then a Hadamard, then we can just measure both of these qubits in computational basis, and we will know exactly with which Bell basis state we have started. So for example, if we measure 0, 0, like here, and here we both measure 0, it means that it's this state, this Bell basis state. If we measure 0, 1, it's this, and so on. So, which brings us to the conclusion that Bell basis measurement is just like this huge thing on 2 qubits. It's just the same as you have 2 qubits, you apply C0, you apply a Hadamard, and then you measure. And you have these 2 outcomes, which tell you which Bell basis state you would have gotten. So these are just the computational basis measurements. Okay. So that was the first point about the Bell measurement. Now let us come back to the evolution of the state. So we start with phi, with system S in state phi, and then 2 systems A and B, which are entangled. Phi, we just write it out in terms of 0, 1 basis. This we can write out as just square root of 2 alpha 0, 0, 0 SAB plus beta 0, 0 SAB plus alpha 0, 1, 1 SAB plus beta 1, 1, 1 SAB. And then we just have to look, and then A measures S and A, Alice measures S and A in the Bell basis. We just already understood what it means to measure in Bell basis operationally. But for this here, we don't actually need to know that explicitly. And then there are different results that you can get, right? So, for example, then we have to go case by case. So, for example, and see what state would B end up on his end, and then which operation he has to act with on his state in order to get the state alpha 0 plus beta 1. So suppose that A measured 0, 0 plus 1, 1 over square root of 2, like this SA. To understand which state B has ended up, And on his side, we need to use the update rule. So the update rule would just be that the projector, which corresponds to this measurement, which is just 0, 0 plus 1, 1 square root of 2, 0, 0 plus 1, 1 square root of 2. These are all SA. By the state, which we'll call psi SAB, psi SAB, and over the trace of this thing above, so that the state that we will get in the end would be normalized. But let us forget about the trace for now, because we can just apply this update to the state of S, A, and B, and then we will see in the end, like, just normalize it in the end. Okay, so let us compute this. So what we get is 0, 0 SA plus 1, 1 SA over square root of 2. And here we have this bra, the sum of two bras, acting on the psi, which is a ket. And I'll take 1 over square root of 2 out, so it wouldn't be a problem. 0, 0 SA plus 1, 1 SA. Yeah, actually, I'll take square root of out of psi and also out of here, so I'll end up with 2. But again, I don't care about factors here so much. It's more about the bras and kets. The factors we can normalize in the end. And here, I'm going to write this. So I would have more space. And here we have psi SAB, which is alpha 0, 0 SAB plus beta 1, 0, 0 SAB plus alpha 0, 1, 1 SAB plus beta 1, 1, 1 SAB. Okay, and let us analyze this sum. So if we contract this bra here, 0, 0 SA, with each of the bras in the on the right side of the expression. So for example, if the 0, 0 is contracted with this bra here, which is just 0, 0 SA tensor product 0 and B, it will give us 1. However, if it's contracted with the second term in the expression, which contains 1, 0 SA, it will get 0. So this actually will not give any contribution with respect to contracting to 0, 0. This as well. And this, because it's 1, 1, then it also will not give any contribution, because 1, 1 is orthogonal to 0, 0. The same reason. Essentially, then for 0, 0, only this term survives. And it gives us alpha 0B, because we have 0 here for B. Okay, then let us analyze the second term. I don't know which color to choose. So 1, 1. Again, with the first term, doesn't give anything because here is 0, 0. With 1, 0, also doesn't give anything because 1, 1, 1, 0 gives 0 because of 1, 0 of A. And here, 1, 1 and 0, 1 also doesn't give anything. Finally, here in the last term, it gives us it finally contracts and gives us 1 identity. And for the system B, it then just gives us 1. Because we have 1 here. Sorry, B. And of course, then also the first part of the equation stays 1/2, 0, 0, 1, and that is A square root of 2. Yeah, and here the normalization would just give us 1 part of SA square roots, and here so we see that B on his side, after if A has measured the state of the Bell basis, B on his side will get, on his qubit will get this state, which is exactly phi B. Which means that if Alice got 0, 0 plus 1, 1 over square root of 2 after measuring systems S and A jointly, then Bob does not have to apply anything. He already has the state phi. One can also analyze then what happens if Alice got 0, 0 minus 1, 1. You can do the similar analysis, and what we will actually get, just for this one I'll give a hint, is that you arrive to the state 0, 0 minus 1, 1 over square root of 2, alpha 0 minus beta 1. What does it mean? It means that, so this is SA, it means that Bob has to apply something that would turn beta, like sine of minus beta to beta, right? So we need to apply something that would turn our alpha 0 minus beta 1 to alpha 0 plus beta 1. Which operation is this? This is actually a Z operation. This is a Z gate. And then if Alice got, for example, 0, 1 plus 1, 0, then Bob has to apply something else. And the last one, it's a 0, 1 minus 1, 0. Bob has to apply this something else, something different from the previous ones. And the operations that we're looking for, they are contained, so the U that he has to apply, they're contained in the following set. So it's X, Z, and identity. And you just have to write down which operation corresponds to which result that Alice gets. And then you will completely understand this teleportation protocol that exists in quantum information. Yeah, the idea of this protocol, as I said in the beginning, is that if two parties share an entangled resource, an entangled state, that can be a resource to kind of teleport the information about the state from Alice's lab to Bob's lab. Okay, I think these were all 4 exercises from the exercise sheet. Yeah, so do you have any questions about this sheet or previous ones? Yeah, maybe while you're still writing the questions or coming up with questions, yeah, I'll emphasize that, like, for this course, it is important to understand how circuits work, because that probably will be one of the questions of the exam, maybe to analyze some kind of small circuit. Again, you don't need to take all the integrals that you have in a course by hand. You can also use some software. Yeah, I think that's all the comments that I wanted to make. Okay, if there are no more questions, then yeah, you can always write me an email. I might be a bit delayed in answering the email, but I should answer it within like 3 days or so. Yeah, then thank you for coming, and I hope you enjoy the rest of the week.